Dear friends, welcome to the channel Total Output Power Solutions. I am Manohar Tatvavadi, and in this video we will discuss about the performance of heaters in turbine steam cycle. So feed water heaters in a regenerative cycle, the steam is extracted from steam turbine at various stages and it is used to heat the feed water. This results in a higher cycle efficiency by increasing the temperature of the feed water inlet to the boiler and reducing the amount of energy lost in the condenser. The design considerations are the number of feed water heaters used in any specific steam turbine cycle depends mainly on the size of the turbine, the inlet and exhaust steam condition, the plant cycle, and economic consideration. The types of feed water heaters, there are two types: open type, where the extraction steam directly mixes with the feed water that is to be heated, that is, you can say, Deaerator. Then closed type heaters, which maintain a separation of extraction steam and feed water to be heated, are called as feed water heaters. The design considerations: feed water heaters, LP heaters, these heaters are either of closed type or open type and extraction steam at a low pressure or subatmospheric pressure. Generally, condensate at a low pressure is heated in LP heaters. HP heaters. These heaters are closed type and extraction steam at a higher pressure is used to heat feed water at a very high pressure. Here you can see in the diagram, these are the LP heaters. Now the first of all you will see the green thing, the condensate flow. So the green pointer, you can see the condensate flow from gland steam cooler to LP heater number 1, LP heater number 2, LP heater number 3, and then it will go to the Deaerator. Then the drip, the drain of the heaters. So the drain of the heaters, you can see it is blue color. From LP heater 3 it will go to LP heater 2, and from LP heater 2 it will go to LP heater 1 and then to the drain cooler. The position of the drains may change depending on the load that is being shared. If the load is full, then this would be the condition. The red pointer here, you can see they are the extractions. So extraction number 1, 2 and 3. Extraction number 1 will go to LP filter 1, number 2 will go to LP filter number 2, and number 3 will go to LP filter number 3. So these are the low pressure heaters where the condensate from CEP discharge at a low pressure is heated further in LP heaters with the steam extracted from the turbine cycle, and hence they are called as low pressure heaters. The HP heaters, here you can see there are two HP heaters, HP heater number 5 and 6. The first of all we will see where the from where the feed water is being heated. So feed water from BFP discharge is going into the HP heater number 5, you can see, and then it goes to HP heater number 6 and then to the feed control station and then to the economizer boiler inlet. This is the feed water. Then you can see the drain as well. You see the drain of HP heater number 6 is going to HP heater number 5, and then from HP heater number 5 it goes to HP drain flash tank. The drain may be diverted to the Deaerator also, and the HP heater number 6 drain, that can also be diverted to HP drain flash tank. Now the drain drip diversion, it depends on all the level control. So the control valves are level control valves. Now the extraction number 6, 5 and 6. The extraction number 5, 6. You can see the red balls. So the red balls, that is the extraction for HP heater number 6 and HP heater number 5. So these are the extractions. So feed water at a high pressure is heated before the feed water enters the boiler economizer with the steam extracted from the turbine cycle, and hence they are known as high pressure heaters because the feed water is at a very high pressure. Then extraction of steam, and now here you will see the LP heater drains and cascading of drains. You can see the HP heater number 6 drain goes to HP heater number 5. HP heater number 5 drain goes to the Deaerator. Then the LP heater number 3, that drain that will go to LP heater number 2. From LP heater number 2 the drain will go to LP heater number 1, and from LP heater number 1 it goes to the drain cooler and then the LP drain flash tank. The extractions are also there. Extraction number, that is LP heater number 1, LP heater number 2, extraction number 2, extraction number 3, extraction number 5, and extraction number 6 going to LP heater 1, 2, 3, 4 and 6, 5 and 6. 1, 2, 3, 5 and 6. So the drip is the extracted steam from the turbine cycle condenses after giving its energy to the condensate or the feed water, that is called the drip. The drip flows from high pressure to a low pressure of the extracted steam. Now the typical feed water heater you can see here, you have a feed water inlet and feed water outlet. There is a partition plane, and then the feed water flows through the tubes from the subcooling zone to the desuperheating zone. It shapes like a U shape like that. Subcooling zone to desuperheating zone, and then it goes to the feed water outlet section. The parting plate is there. Then the actually the extraction steam is supplied at a point here. The extraction steam is supplied. Then there is a desuperheating zone, and then the steam passes over the subcooling zone. There is a gauge glass which is showing you the water level, because there is some the condensate present in, means cooled, the extraction steam as it gets cooled it will create some condensation, and that level is being maintained there. The drain outlet, it is also shown here. The drain outlet is from that point. Now the HP heaters, they have a direct impact on machine reliability and plant heat rate and efficiency. The heat rate loss in a 210 megawatt unit, in case HP heaters are not in service, is about 68 kilocalories per kWh. Now if we want to have the performance testing, so the operating conditions for performance testing would be, the unit operation should be at a rated load. It's a 210 megawatt load, so we will maintain 210 megawatt load. The stabilized operating conditions means the unit must be running at 210 megawatt load since around an hour or so. So the levels, they must be set as per the test requirement. The levels, heater levels, they are to be set as per the test requirement. The drain cascading system, that should be normal. The drain cascading system means the drain that is going to that is being cascaded, that should be normal. Then the heater vent valves, they should be kept open or closed as per the operating instructions. Whatever the operating instructions are there, so they should be opened or closed. Well, then while collecting the heater wise parameters, heater number 5 and heater number 6, we will collect the following data: unit load in megawatt, main steam pressure and temperature and flow, then feed water flow, superheater and reheater attemperation flow, boiler feed pump discharge pressure, HP heater levels, condenser vacuum and barometric pressure. Then the following readings we will take down: the feed water inlet temperature in degrees centigrade, feed water inlet pressure in kg per square centimeter, feed water outlet temperature in degrees centigrade, feed water outlet pressure in kg per square centimeter, HP heater shell pressure in kg per square centimeter, HP heater extraction temperature degrees centigrade, HP heater extraction pressure is kg per square centimeter, HP heater drain temperature is degrees centigrade, and feed water differential pressure is feed water inlet pressure and outlet pressure, that will be differential pressure, that is in kg per square centimeter. So these are the readings we will take down. The design readings are all, the design parameters are also there, and we will note down the actual parameters. for heater number 5 and heater number 6. Now the performance of HP heaters, it can be analyzed by the by monitoring or trending the parameters, the terminal temperature difference, that is the TTD, then the drain cooler approach, the temperature, that is DCA, then the pressure drop on the feed water side, and the feed water temperature rise across the heater. The terminal temperature difference, TTD, and drain cooler approach. So these are the two terms which you require to be very careful about. The terminal temperature difference is the difference between the saturation temperature of steam corresponding to the shell pressure Ts and the feed water outlet temperature TO. So this TTD will be equal to Ts minus TO. The drain cooler approach, DCA, that is the difference between heater drain outlet temperature and the feed water inlet temperature, that is DCA, drain cooler approach, that is equal to TDO minus TI, inlet. Here you can see the shell pressure, the heater shell pressure, and the temperature, the saturation temperature corresponding to the shell pressure will be the Ts. Then the feed water outlet temperature is shown there, feed water inlet temperature, and the heater drain out temperature. The terminal temperature difference, TTD, that is the difference between the temperature of steam corresponding to shell pressure and feed water temperature, TTD, Ts minus TO. So typical design values for HP heaters with de-superheating zone should be naturally 0 degrees centigrade to -2, around -2 degrees centigrade. The TTD measures the heat transfer efficiency of the heater. An increase in TTD suggests that the heater is not performing well, leading to higher heat rate and reduced efficiency of the plant. The drain cooler approach is the difference between the heater drain outlet temperature and the feed water inlet temperature. The lower DCA, drain cooler approach, indicates better performance, while the higher values suggest for low heater levels. So the heater levels may be low for that. So typically it should be, DCA should be 5 to 10 degrees centigrade. If the DCA is too high, it may cause erosion and damage to heater tubes, baffles, and the drain cooling zone. The factors which affect the HP heater performance: the tube fouling, reduced, it may be shown by reduced feed water temperature, then uncontrollable increase in heater level. It may cause potential damage to the turbine also if the level goes too high because of tube fouling, because the pressure is very high, the feed water pressure is very high, so it may cause potential damage to the turbine. Failure to vent non-condensable gases. If you are not venting, or if it is not vented properly, then the non-condensable gases deposit on the tubes and thereby reduce the heat transfer. So this will cause an increase in TTD, and hence non-condensable gases must be removed or vented. The changes in the heater level. The optimum level of performance shall be decided by the minimum DCA. This you should finalize, the DCA. The control valves and the level switches, instrumentation, it must be checked for that. The control valves and the level switches, they must be checked. The partition plate, sometimes the partition plate may be passing, so this will bypass the heater. The feed water outlet temperature will be reduced. Heater bypass valve, if it is passing, that will be same as above. This will bypass the heater and the feed water outlet temperature will be reduced. The heater performance deviation. Check the following if TTD, DCA, and the temperature rise are deviating from the design and actual rise in feed water temperature is low. So high terminal temperature difference, TTD. This may be due to excessive heat venting because of worn vents, altered set point, or vent malfunctioning. Then there may be excessive makeup, because of which there may be high TTD. High water level, tubes leaks may be there, improper setting of the level is there, then that may happen. Header partition leaks. The header partition, if it is leaking, then also there may be a difference in TTD, higher TTD. Non-condensable gases on shell side, if they are on the shell side, then the heat transfer will not be there, or will be uh, heat transfer will be there, but it will reduce, and that will cause the again the TTD to go high. Excessive tube bundle pressure drop. So excessive number of tubes, if they are plugged, then this may happen, the TTD may rise. So those are the reasons for the high TTD. Now high DCA, high drain cooler approach temperature. The drain cooler inlet, if it is not submerged, that may reduce, it may approach the DCA may be higher. Low drain water level, improper setting may be there, level setting may be there. Excessive feed water heater drain bypass valves may be left open or may be passing. The bypass valves may be malfunctioning, or it may be leaking also. Then the excessive tube bundle pressure drop means excessive number of tubes they are plugged, or the tubes folded internally. The feed water heater, if it is bypassed, then again the DCA will be higher. Feed water heater bypass valve, that may be leaking. So similar approach shall also be followed for LP heaters if you are checking about the LP heaters. Now the performance improvement. For the performance improvement, you must minimize the TTD deviation. You must always check for how you can uh, reduce the TTD. So TTD deviation between 0 to -2 degrees centigrade. Determination of optimum operating level. That means the DCA should be lowest for a particular level settings of the heaters. You should get lowest DCAs. Then deviation in final feed water temperature. It may be because of passing of water box partition plate, maybe because of passing of bypass valves. The final feed water temperature will be reduced. Now monitoring of feed water outlet temperature after top heater and after bypass valve. The operation of unit with heaters out of service. If the heaters are not in service, HP heaters are not in service, then you will have the increased steam flow through the remaining section of the turbine. You may get increased steam flow. For a given throttle flow, turbine output will increase. The turbine cycle heat input increases because of low feed water temperature, but the turbine and plant heat rate are poorer. So thanks for watching. Please like, share and subscribe. Comments are most welcome. Well, I am Manohar Tatwadi taking your leave from Total Output Power Solutions.